Hello and welcome back to Compressible Flow. I'm Professor Steve Miller. Today we'll be talking about isentropic flows and transition a tiny bit and consider shocks in these flows for the first time. We'll look at the particular so-called DeLaval nozzles, which is a fancy word for Convergent-Divergent nozzles, and a traditional way of referring to them. Then we'll look at particular isentropic nozzle operations. We'll then look at a few examples for rocket engines. It's an exciting class because we're starting to apply our theories to the particular problems at hand for nozzles, which are one important aerospace device. Let's start off the class with a fun quote from one of the most famous people in aerospace engineering, Wernher von Braun. He wrote that the rocket worked perfectly, except for landing on the wrong planet. This was his comment on the V-2 rocket landing in London in 1944. This is written and quoted in Apollo in Perspective, Spaceflight Then and Now. Von Braun, Dr. von Braun was a remarkable figure who rose through and developed rockets during World War II and before, of course, in Germany. During World War II, he developed the V-1 and V-2 rockets were used to, of course, bomb the United Kingdom. His ultimate goal was always to take rockets and propel people to outer space orbit and eventually other planets. In Operation Paperclip and beyond, he came to the United States and led NASA and the Apollo program, and without him, the United States would never have likely put man on the moon. Here is a picture of a cow. You might be asking yourself, what do cows have to do with aerospace engineering? I've put this particular figure, which I've labeled the DeLaval company cow and logo, in background. You'll see the logo up top, DeLaval. And it's very much possible that this particular cow loves aerospace engineering. I wouldn't have any doubt about it. And you might be wondering now, in this aerospace engineering class on compressible flow, what does a cow and the dairy industry have to do with aerospace engineering? Here's the description from the company website. It says, DeLaval is a worldwide leader in milking equipment and solutions for dairy farmers, which makes sustainable food production possible, ensuring milk quality and animal health. DeLaval's solutions are used by millions of dairy farmers internationally every day. DeLaval was founded more than 130 years ago in Sweden, when the visionary Gustav DeLaval patented the cream separator. Today, DeLaval has 4,500 employees and operates in more than 100 markets. DeLaval, alongside Tetra Pak and Sidel, is part of the Tetra Laval group. So, of course, it's no longer a standalone company. This quote was taken from their website in 2019. DeLaval himself was an amazing engineer and played an important role in creating one of the most important devices that powers rockets and aircraft engines and many other aerospace devices today. Let's take a second to appreciate Carl Gustav Patrick DeLaval, which is pictured on the right. I think I see a few haircuts around campus, just like Gustav's on the right. You'll see that he was an engineer, inventor, and contributed to the design of steam turbines, which is a big key in dairy machinery. He enrolled when he was pretty young at the Institute of Technology in Stockholm. Later, the Royal Institute of Technology, or called KTH, in 1863. I had the honor of actually going there during a conference and giving a seminar. He received his degrees in mechanical engineering in 1866, like some of you are today, and he was in the Royal Society in Sweden in sciences, and he also held a position in Parliament, so he was a very multivalent person. Most important for this class, in 1890, he designed and created a nozzle to increase the steam jet to supersonic speed. And you see the connection now, because of course in the previous classes we looked at choking and accelerating flows to supersonic Mach number. He passed away in Stockholm, which is a beautiful city, in 1913. A few other notes on DeLaval. He is the real origination of the Convergent-Divergent nozzle. He designed Convergent-Divergent nozzles for steam turbines to power dairy machinery. In the previous class, we looked at another of the company's designs for, of course, choking flow through a particular system of butterfly valves and a choked convergent nozzle to control mass flow rate exactly. Indeed, he was Swedish and he worked in industry and mining and left for his Ph.D., which was probably a good decision at the time. He started his own company in Stockholm that made cream separators, and he held these Senate positions. What's interesting about DeLaval is he did this work intuitively, physically intuitively. Indeed, he had no knowledge, or at least any proof that we have at the time, that supersonic flow actually existed inside nozzles. This was not proved experimentally or really mathematically until many years later, of course, in the laboratories of Prandtl in Germany. Here's a picture of his original patent. You'll see this is a turbine. There's a shaft which is labeled C. There's a rotor which is attached to the shaft which is labeled D. There's a system of nozzles which are not connected to the rotor, and the rotor has a system of turning vanes. These little nozzles, 4 of them in the cream separator design at least, allowed superheated steam to travel down through the plenum, where my cursor is, through a convergent portion of the duct, through a choked condition, and then expands out and blows through, of course, the turbine, which rotates the turbine. This has increased the power and efficiency of these particular turbines, which made his company world known. What's interesting is he did this design intuitively. He had no real physical understanding and justification of why this was working. This was done, once again, as I mentioned later, by Prandtl's group in Germany. Let's look at a more contemporary design from, of course, the DeLaval nozzle, which just refers to a converging-diverging nozzle. This is a picture which I took from NPO Energomash in Russia. This is a Soviet company which still exists today under an umbrella company in Russia. This particular engine is the RD91 engine. Beyond all the ductwork above, you can see that inside there's a combustion chamber, which is essentially a large plenum, and then there's a throat or choking area where a critical condition occurs, and then the cross-sectional area of the nozzle increases to accelerate the flow out to the exit of the nozzle plane, which is this bottom part in the cursor. So we have gone from, in less than a few decades, from cream separators to high-performance rocket engines. Here's a picture of a series of rocket engines developed in the Soviet Union and Russia by NPO Energomash. This is their floor models. I had the fortune of touring this facility before it was open to Westerners when I was younger. You can see what's interesting about this facility is there's many different rocket engines, and from the combustion injector plate in each part of the plenum, for each of these types of RD nozzles, you can see that there's, of course, a cross-sectional area which decreases. The flow goes through a convergent part of the nozzle. It is choked at Mach 1 and then is accelerated by increasing the area. You might be wondering, well, why don't we design the areas to be more aggressively increasing? Because that would decrease weight. Well, there's a lot of reasons for that when we'll talk about later in the class. For now, we'll just consider one-dimensional isentropic flow and get into shock waves. And I think you'll see this is much more complicated than, of course, one-dimensional isentropic flow. Here's another example from the United States. This is the F1 engine of Rocketdyne and its cutaway, and this time we can actually see in the engine. So up here we have our injection plate. We inject fuel and oxidizer, which combusts in the combustion chamber, and we have only a very small cross-sectional area decrease, which accelerates the flow from the plate through a choking condition, and a very, very long and increasing area divergent part of the nozzle. We call these traditionally the DeLaval nozzles or Convergent-Divergent nozzles. They all operate on the same principle of taking a high pressure, high temperature gas and accelerating it and choking it and accelerating it out and taking the internal energies of the flow, the energy of the flow, and converting it into a kinetic energy, which of course creates thrust. You'll see contemporary aircraft engines also use the same principles. It's all the same principle of taking the flow and efficiently converting as much of the internal energy as possible from the combustion process into the kinetic energy, which creates thrust. You can, of course, assess these types of engines with the basics of Reynolds transport theory, which we already introduced. by, of course, using a combination of isentropic theory to take the internal energy into kinetic energy, and then doing a control volume approach with appropriate mass flow rates of injection for fuel and oxidizer with its exit velocities to find thrust. We'll try some of these problems in this class. Here's an even simpler diagram of the approach I talked about. We have a plenum. In this case, it's a combustion chamber. We are injecting fuel and oxidizer, which we combust, and it creates high temperature, high pressure gas. And of course, it's all its reactants. It will move from left to right, because that's the only way it can go once the engine explodes, and it'll be subsonic speed. That subsonic speed will accelerate to higher Mach numbers through the convergent part of the nozzle, and it will, of course, become transonic, m equals 1, if the pressure ratio is high enough, and I'm sure it is in this case. It will accelerate out the nozzle exit with increasing area to supersonic speeds. This is the advantage, of course, of the converging-diverging nozzle. If we only had a converging nozzle, meaning we take away the divergent part, you'll see that our exhaust Mach number would only be limited to 1. So by adding all this weight, we gain a tremendous advantage in thrust. It's worth the cost of weight because we've created a high-speed, high Mach number flow, which increases thrust, and extract more of the internal energy of the flow into kinetic energy. This makes sense. Here's one more example. This is a Russian-type military rocket engine, and this is a cutaway, which corresponds exactly to the previous figure. The injection ports are on this panel. This is, of course, the plenum where combustion happens, and its reactants are high pressure and high temperature, come down, choke at the minimum area, and are accelerated out to flow. By this picture, you can actually estimate the area ratios A over A sup star from the exit, area exit over A sup star, and you would in fact be able to estimate the design Mach number and performance of the engine. And you can get very specific if you knew the particular fuel that the engine uses. Let's look at one example of this particular case for this particular engine. Once again, there's a minimum area, and we label that A sup star, which is the critical or choked area. It has a Mach number, m sup star of 1 by definition, and U sup star, the velocity at the throat of the nozzle, will be, of course, A sup star, which is the speed of sound at the throat. At any other position, we've developed our isentropic tools, at least, to estimate the Mach number velocity and area. Remember, through the Mach number area relation, we can find out the Mach number at any other area relative to the choke condition, and from that Mach number and other thermodynamic conditions of P naught, T naught, etc., which are constant through the nozzle for isentropic flow, we can calculate all other thermodynamic and field variable properties. Fascinating. Let's return to the derivation of the Mach number area relation to put it in a form which is a little bit more useful for the nozzle problem and problems alike it, which we'll use through this class. We'll again seek the Mach number area relation. Please remember that we can choke the flow at the minimum A. If the flow is choked, and it doesn't necessarily have to be, but if it is choked, we'll call that area A sup star, the critical area or area of a choked flow, minimum area in a converging diverging stream tube. Recall the conservation of mass. Rho UA equals rho UA at station 1 and 2. We'll just let station 1 be noted by sup star. So rho sup star, U sup star, and A sup star in equation 264 of this slide deck corresponds to the density, velocity, and area at the throat of the nozzle, which is right here. The right-hand side, rho UA, will be any other position marked in A as a function of x, for example, from, say, the inlet or outlet of the nozzle. A is only a function of x in this case. It has area, Mach number, and velocity. So now we've balanced the mass conservation. Now look at the left-hand side and note that because m equals 1 at the choked condition by definition, we can write U star equals C star through the equation m equals U over C, or 1 equals U over C, therefore U equals C sup star. Let's substitute that into our equation and solve for A over A sup star. So that's what we have in equation 265. And let's simplify that a bit. We'll write A over A sup star equals rho sup star C sup star over rho U. We can then write rho sup star of rho naught C sup star over rho naught rho U. I've put in, of course, rho naught over rho, and you'll see why in a second. Recall that we previously developed an isentropic and stagnation values are constant in an isentropic flow. This means if there's no losses in this particular nozzle, if it's designed in a specific way, which we'll discuss later, that the flow through the whole nozzle from Mach number 0 through a high Mach number is isentropic. You'll see in this particular case that the stagnation conditions at any area cross-section are constant. That means the stagnation density, rho naught, stagnation temperature, T naught, and the stagnation pressure, P naught, are constant through the flow. So we can write and use our critical condition we previously developed for rho, and we can write rho naught over rho sup star, that's the stagnation density, divided by, of course, the critical density, equals gamma minus 1 over 2 of 1 over gamma minus 1. See why I developed this relation related to 265 in our recollection. We developed 266 in a previous class. Also recall that we developed a relation for C sup star. Remember, M equals U over C. Therefore, U over C sup star squared goes as M star squared. And we develop our critical condition of M for 1 goes as gamma plus 1 over 2 m squared all over 1 plus gamma minus 1 over 2 m squared. So that was also from our previous class. Now we might imagine we can square the equation involving the ratio of A over A sup star, 265. And we would therefore square each terms according to the laws of algebra. We'll now have A over A sup star squared goes as rho star, rho naught squared, rho naught rho squared, C star, U squared. Now we can easily substitute our relations of U over C star squared and rho naught over rho star into 268, and we'll find equation 269 on the slide deck. And now we'll have A over A sup star squared equals 2 over gamma plus 1 over 2 over gamma minus 1 times 1 plus gamma minus 1 over 2 m squared for the second term. And the third term from 268 to 269 is 1 plus gamma minus 1 over 2 m squared all over gamma plus 1 over 2 m squared. Let's now try and simplify equation 269 on the slide deck to something a little simpler, which I've done for you, and you're welcome to try this yourself. We now have a beautiful form of the Mach number area relation for a choked flow. It goes as A over A sup star squared will go as 1 over m squared times the quantity of 2 over gamma plus 1 of 1 plus gamma minus 1 over 2 m squared in quantity of gamma plus 1 over gamma minus 1. Look at this equation carefully. You'll see the most familiar term in this class of 1 plus gamma minus 1 over 2 m squared. We see this term coming up over and over. And in fact, this is no coincidence. You'll see in the isentropic tables, which we formulated and given in the class handouts, you'll have one column in isentropic table for A over A sup star, and you'll have the first column as Mach number. Therefore, you can easily evaluate this equation for Mach number or area ratio, as long as the flow is choked. That's meaning of A sup star. We now have the all-important Mach number area relation. This equation, remember, shows M is function of plus or minus A over A sup star. This is a function. There are two values indeed of M corresponding to the solutions of this equation as we discussed earlier in a slightly different form of the area Mach number relation and its derivation. These relations of all these values, including A over A sup star, are tabulated in the famous isentropic tables of NASA Ames, the so-called Ames tables, which I've put in as a file, an original PDF copy in your class handout. And some of the graphs in the class handout with the tables are photocopies, essentially, attached to the tables. Remember, there are no mathematical or physical solutions for A over A sup star is less than 1. Let's look at a graph of this particular solution in a few moments to understand the physics of it. Here's a beautiful graph, which I photocopied, of the Mach number area relation which we just derived for gamma 1.4. Indeed, figure 89 states that the graph of the Mach number area relation is here. On the x-axis, we have the area ratio A over A soup star. Indeed, because the flow is choked, we can never have an area that's meaningful in terms of the equation due to its assumptions of A over A soup star less than 1. Here, on the x-axis, we have Mach number. The lower part goes from Mach number 0.1 to 1, and the upper part is Mach number 1 to 4. Obviously, that line here through the middle, horizontal line through the middle of the graph, represents the division between subsonic flow and supersonic flow. There's nothing below area ratio 1, and this is why there's a line, vertical line, that goes through the transonic condition of A over A soup star. Basically gives us Mach 1. You can try this out in this equation yourself. Put in m equals 1, and you'll find that A over A soup star squared equals 1. Therefore, A over A soup star is equal to 1. That's what you're finding on this table. So if you evaluate it yourself for fun, you'll find that if you don't have this condition, then you have made an error. It's certainly not an error in the analytical formulation. For this particular table, we varied A and found a multivariable solution, multi-value solution for Mach number. So for example, A over A soup star of 2 has a subsonic Mach number about 0.3 and a supersonic Mach number about 2.2. What does this mean? Say we have a DeLaval nozzle that accelerates flow. There's subsonic flow in the convergent part of the nozzle, which would correspond at, say, maybe some area A over A soup star. It would have of 2, it would be 0.3. And if it has a area of the exit over A soup star, that's the area of the exit of the nozzle divided by the area of the throat, of 2, then we would have an exit Mach number, not fully expanded Mach number, which we'll talk about later, of about 2.2. So do not confuse exit conditions of devices with fully expanded conditions, and we'll discuss more about these subtle differences later in the class and through your homework. Let's look at a graph of this with respect to a nozzle. Here's figure 90. We show the variation of Mach number in a typical convergent-divergent nozzle with a particular transonic throat. In this particular condition, the walls are drawn with a notched line, and the flow moves from left to right. Here's the plenum, where the Mach number is very, very small. Here's the throat, where the flow chokes, where we achieve m equals 1, and the area of the throat, A sub t, equals A soup star. And the flow accelerates at higher speeds and becomes Mach number greater than 1. Remember, the Mach number area relation analysis dictates if the flow accelerates or deaccelerates in divergent or convergent parts of the flow, respectively. Up here, we're just saying the area of the inlet, which we denote as A sub I over A soup star, which is the reference area, the choked area, is very, very large. We say it goes to infinity. At the exit of the nozzle, which is defined as A sub E, the area of the exit of the nozzle A sub E, all over A soup star, which is the reference choked area, is a particular finite quantity, which is right here. Note that the Mach number downstream in the exhaust of the engine or nozzle can be even higher because the flow continues to expand as if there was an invisible nozzle there, dictated by the particular shear layer of the jet flow. Now in this case, we have some stagnation conditions. The combustion process or turbine or whatever is in front of the nozzle device, or a wind tunnel even, has a particular stagnation densities, pressures, and temperatures. We'll denote that as P naught and T naught. Now this is an isentropic flow through the nozzle. This means that P naught and T naught are constant through the whole flow and even out into the exhaust of the nozzle, until there's turbulence, of course, in the nozzle exhaust. We denote the throat as m equals 1 for transonic condition and A sub t equals A soup star. We might ask ourselves, how does Mach number vary in this particular flow? Well, it varies according to the area Mach number relation, which in this graph is equation 520, but in this class, of course, is equation 270, or which is graphed in figure 89 of the slide deck. So let's see. We start from about a creeping or very slow speed subsonic flow of Mach about 0. And on the x-axis of figure 90, we have the x-axis, which corresponds to the x-axis of the nozzle, and the y-axis is Mach number. This dashed line here, vertical, between the graphs of Mach number in x and area and the nozzle geometry, corresponds to the transonic or choked condition. You can see by definition that has a Mach number 1 on the y-axis. The y-axis is Mach number from 0 to some high value. The flow starts from 0 and it gradually increases and becomes transonic and choked at the nozzle throat, and then increases its Mach number as we move downstream. Now, it's very rare to have a convergent-divergent nozzle with a Mach number that continuously varies smoothly. If it does, of course, it's an isentropic flow. In reality, things are much different, and we'll start to transition to those cases in this classes. Before we do that, of course, let's look at the graphs of P over P naught and T over T naught in these particular flows. And you should be able to draw these graphs yourself. They might appear on exams or homeworks. In figure 91, I've shown the variation of static temperature T and static pressure P within the convergent-divergent nozzle of figure 90. You'll see, once again, there's a dashed vertical line. That dashed vertical line corresponds to the throat or choking condition of the nozzle where M equals 1. So here, in figure 91, the top we have P, the static pressure, over P naught. You'll notice it's at 1 at the plenum. That's because Mach number is very small, if not 0, in the plenum of the nozzle. And so we'll write P equals P naught, which is 1. The flow will accelerate, and P naught is constant through the whole nozzle, so P will decrease, and the critical value, which we showed when we talked about critical values for P over P naught, for gamma 1.4 is always 0.528, no matter what. So you'll always have this ratio, which is only dependent on gamma, because M equals 1 in every particular situation. So that all that can change this particular ratio is the Gauss constants and ratio of specific heats. You can also see the same graph for temperature, T over T naught. Once again, you'll have a critical value of 0.833, which is only dependent on gamma for calculated perfect gas. After the flow chokes, the Mach number increases even more, and the static pressures and temperatures continue to decrease. We've shown the particular equations of P over P naught and T over T naught, which are functions of 1 plus gamma minus 1 over 2 times m squared, our old friend, which is in so many equations in this class. You'll notice the powers are inverted, as of course we have P over P naught and T over T naught, and you'll see on your equation handout that we show T naught over T and P naught over P. This is because we often want to seek total values or stagnation values in our problems, and it's easier this way so we don't have to invert the problem as a second and unnecessary mathematical step. However, for graphs of these problems, we often show T over T naught and P over P naught, which is customary and traditional in rocket engineering. Now, you might be thinking, what happens if the area of the throat is not choked? Then we entirely have a subsonic through the nozzle, and it's much more common to have an isentropic flow through a convergent-divergent nozzle that's operating subsonically. Generally, there's not much point in life to having a convergent-divergent, that is, a DeLaval nozzle, that is operating subsonically. But there are a few situations which maybe we can look at later in this class. So ideally, the flow in the nozzle expands isentropically. Remember, this is not always the case, and it's not always the case that we hit the transonic or choked condition at the nozzle throat. Take a look at figure 92 shown here. Once again, we have a total pressure in the plenum with corresponding density total pressure and static total pressure at a low Mach number. There's an area of the throat in the converging-diverging nozzle, and the direction of the flow is from left to right. There's also an exit pressure. We'll write that as P sub E. This might be viewed as a back pressure in a subsonic flow of the nozzle. P sub E is not necessarily equal to the ambient pressure outside the nozzle for some cases, especially in supersonic flows, which we'll talk about later in this class for nozzle exhaust. Nonetheless, the subsonic flow through the nozzle is pressure-driven from a total pressure P naught to a static ambient exit pressure P sub E. This pressure ratio, P naught over PE, needs to be large enough to drive the flow to the supersonic conditions at the exit and choke the flow at the throat. Indeed, if P naught over PE is small, and it's always above 1, it could be like, say, 1.2, for instance, P naught over PE, then the flow is likely subsonic. In this case, the flow field is very much different than the subsonic case. Let's take a look at it. Here's plots for subsonic isentropic flow through the isentropic nozzle. Compare these to the previous plots that we just showed in around figure 90 and 91. This shows the variation of flow through the convergent-divergent nozzle, which we just showed, in a subsonic and transonic regime. Let's look at the first figure to understand the Mach number. The x-axis is from 0 to a large value, which corresponds to the nozzle exit on the right and the nozzle plenum on the left. The dashed line that's vertical through the graphs, once again, is of course the condition where the area is smallest, which is the nozzle throat. We might achieve on the upper figure a Mach number from 0 to m, where m is 1 would be transonic. That's line 3. Line 1 has a very, very, very small ratio of P0 over PE. And you can see it grows, the Mach number increases, and then it's subsonic, it never chokes, and then the Mach number decreases again through the divergent part of the nozzle. If we increase the ratio of P0 over P, then we'll reach, of course, a value of line 2, but it's still subsonic. And if we increase the ratio of P0 over P even higher, eventually we'll hit the transonic condition. At some point, we have a multivariate solution. At this particular case, if we hit transonic condition and the pressure ratio is just right, we'll once again deaccelerate down to a subsonic Mach number, ME sub 3. Here, sub E means exit. So we have Mach number at the exit of 1, 2, and 3. ME1, ME2 is subsonic. ME3 is subsonic, even though we have a transonic condition at the throat. Let's look at how the pressure changes relative to the previous figures of the supersonic cases. For low values of P0 over PE in 1, the static pressure will go from 1, it'll decay a little bit, and then the flow will deaccelerate again, and we recover the static pressure in the divergent part of the nozzle. So you can see it very much acts like a diffuser. In this case, the divergent portion of the nozzle is subsonic flow, therefore it is very much a diffuser which deaccelerates the flow and recovers our thermodynamic variables in an isentropic fashion. In that sense, it's a perfectly ideal diffuser. If we increase our pressure ratio a tiny bit more, just a tiny bit more, then we'll have a slightly faster subsonic flow and slightly faster subsonic flow than the first case in terms of Mach number. But we have a larger dip in static pressure. So the static pressure will decay more relative to the first case, and we'll have a little bit less static pressure recovery. We would have to expand the exit area ratio even more, AE over AT. Notice I never said AE over A sup star, because A sup star would correspond and denote that the nozzle flow or the convergent-divergent stream tube is indeed choked. Once again, line 3 indicates that the flow has choked at the nozzle throat, which we call A sup star. We would then have P over P0 goes down to the critical condition, same one, 0.528 for gamma 1.4, as we saw in the supersonic case. But we just arrived at the condition, and the pressure ratios are like epsilon off to have the flow return to subsonic and have the divergent part of the nozzle act again as a diffuser. It's a beautiful transonic flow, which is very hard to obtain in the laboratory. I would have to be very careful and carefully use and adjust with a computer the ratio of P0 over the exit pressure, meaning I'm really controlling the total pressure in the plenum of the nozzle, to achieve this beautiful subsonic transonic flow through the whole nozzle. Remember, there's essentially 4 types of flows you can obtain with a convergent-divergent nozzle or stream tube, which we showed in previous classes. Let us be careful and make some notes about subsonic, entirely subsonic flow through the isentropic nozzle. For these cases, we might say that a reference area is only the throat area AT, but we can never use the A sup star values in the table because they have the built-in assumption that we've reached Mach 1. Therefore, you cannot use A over A sup star values, like is the Mach number area relation for a choked flow. This is because, of course, the flow is not choked, so please be very careful when you're doing your analysis not to make this particular mistake. Now, a subsonic flow can often encounter a diverging duct. Remember, in this case, the flow will slow down according to the traditional area Mach number relation. As I noted, the divergent section in these nozzles, or converging diverging stream tubes, acts as a diffuser. And diffusers' objective, unlike a nozzle, is to slow down the flow and recover as efficiently as possible all thermodynamic variables of pressure and temperature, and recover that internal energy. It's taking the kinetic energy in the flow and trying to preserve it without losses and convert it to internal energy, like, for example, enthalpy. You will see that there is indeed an infinite number of isentropic solutions or flows for the convergent-divergent cases. You'll see that I can have an infinite number of lines or possible isentropic flows between 1 and 2, as an example. That's not necessarily true for supersonic flows. Indeed, for DeLaval nozzles that have convergent-divergent properties, there's only one solution that corresponds to the isentropic case. Not only that, the nozzle shape itself must be carefully designed using a method called the method of characteristics, which we'll talk about later in this class in a single lecture. It is very complicated, and you'll see that for an isentropic convergent-divergent nozzles, it must be designed with method of characteristics for an isentropic solution. You can also have convergent-divergent nozzles that are supersonically operating, but of course they'll have losses in them, and they'll have systems of expansions and shock waves possibly in them. There's only one isentropic solution for the entire nozzle with exhaust flow. You'll see that non-isentropic solutions, and there's a whole family of them, an infinite family of possible solutions that contain shock waves inside the nozzle. Let's now look at some Schlieren images to give you an example where our isentropic assumptions break down and our analysis cannot be used. Here's one particular Schlieren in figure 94. It shows a normal shock wave residing in the nozzle, which of course causes the flow to separate, and our whole analysis breaks down. Let's look at the picture and interpret it. Remember, a Schlieren image shows density gradients in the flow, and we'll have a lecture, a special topic on Schlieren systems to show you how they're used. On the left is the large plenum. We might make an analysis and assumption that the total pressure and total temperature and total density conditions are roughly constant and the Mach number is very small. The flow moves from left to right, and we have a high enough pressure ratio to choke the flow at the nozzle exit where my cursor is moving. Now the flow will accelerate from transonic condition to supersonic condition through the nozzle. And what you're seeing here is, in the Schlieren, is a number of cross-patch patterns. This is because there's actually waves coming off the wall, and essentially they are not truly forming a perfect isentropic flow due to the nozzle geometry and design. We would actually have to change the wall curvature to cancel out these waves so they're not bouncing off and canceling them out to have a truly perfect isentropic flow. Nonetheless, this is a signification, this checkerboard pattern, of having a supersonic flow. And so we know visually that this is indeed a supersonic flow. It accelerates, and because the pressure ratio between the plenum and the exit of the nozzle on the right is not high enough, a shock wave forms in the nozzle. That is, it is impossible to match the pressure at the exit of the nozzle to the back pressure boundary condition of the flow without formation of a normal shock. That is, the static pressure in the flow, which is supersonic, has no chance of matching the back pressure. Therefore, a normal shock will form in the flow. The normal shock is shown, and the shock wave itself, which we'll define in a later module and talk about these types of physics, as this very, very, very dark line, which signifies that it has huge density gradients, pressure gradients, and temperature gradients. So as the supersonic flow moves from left to right, it goes through the shock wave, and the pressure, the static pressure, almost instantaneously rises, and it then becomes subsonic. The subsonic flow behind the shock wave then matches with the back pressure. Away from the middle of the nozzle, the flow is much more complicated. And in fact, this is a turbulent regime, and the flow has separated off the sides of the nozzle. As the flow moves from left to right on the nozzle, it comes down and it hits a flow phenomenon which is caused by the normal shock. Indeed, this part of the flow is granulated, and it signifies it's highly turbulent and separated. This might indicate that there's some higher wall heating here, and our nozzle might fail. This is detrimental to, of course, a flight vehicle program that uses rockets or engines and propulsion. This is a situation which is not ideal. We are actually wasting huge amounts of energy and killing our propulsion. Ideally, in this situation, our engine control system would want to raise the pressure and temperature in the plenum greatly and quickly to push this normal shock outside the nozzle so that we can have optimal thrust and a supersonic flow through the whole nozzle. Nonetheless, this is a condition which we'll look at in the class, and we'll look at some problems where I ask you to calculate the position of the normal shock wave as a function of area ratio in a Convergent-Divergent, or the so-called and beautiful DeLaval nozzle. You'll also note that the DeLaval nozzle, a few pages back, had straight edges in his patent, just like this nozzle. Indeed, he had to have very high pressure ratios to make sure that normal shocks were not within his nozzles. But when DeLaval started his nozzles in the dairy industry, of course they had low pressures, and he had to raise them as fast as possible to push the normal shock, which at first appears at the throat, downstream and outside of the nozzle. Let's look at some particular graphs so you can understand the physics of normal shocks in the DeLaval nozzles. On the top, we have a particular, in figure 95, the variations of flow within the CD nozzles, Convergent-Divergent, sometimes we say CD nozzle, with a normal shock. So this is no longer isentropic flow. The flow indeed moves from left to right, and the walls of the nozzle are the zebra striping. So here's the plenum on the left. The flow comes along. It becomes transonic. It accelerates to a supersonic Mach number. It goes through a normal shock wave, and it instantaneously becomes subsonic and exits the nozzle to match the back or exit pressure, P sub E. Let's look at the graphs. Here, the throat of the nozzle is not put as a dashed line. The second graph shows the x direction on the x-axis, and the y-axis is Mach number from 0 to m. And we have a dashed line where it represents the transonic condition m equals 1. So here's m. It goes from 0, it increases to the transonic condition, which represents a sup star, and becomes supersonic, which is m greater than 1, and then it hits the shock wave, which is aligned and then with the graph, and it instantaneously becomes subsonic. If there's no viscosity, you can view this as a discontinuity in the equations of motion, which you have not dealt with in your differential equations classes up to this point. It's very unlikely you've even dealt with discontinuities in your equations when you study partial differential equations, if you so take one of these classes. Nonetheless, you can see in the divergent part of the nozzle, when the flow is supersonic, it accelerates and becomes higher Mach number. And when the flow is subsonic behind the normal shock wave, it deaccelerates because we're still in a divergent part of the nozzle. And the Mach number becomes lower and lower to the exit Mach number at the exit of the nozzle. Let's look at the pressure variation in the bottom graph. Here on the y-axis, as I described before, I have a static pressure divided by a total pressure. The x-axis is the direction of the flow within the nozzle. Here, once again, is our friendly, for gamma 1.4, critical ratio, a P over P naught, 0.528. This aligns perfectly with, of course, m equals 1, where we have a choked flow in the CD nozzle. We go from P over P naught equals 1 down to the choke condition. And then, of course, the flow becomes supersonic and pressure becomes smaller and smaller because the flow is expanding. And then we hit the normal shock wave, and the static pressure instantaneously jumps up, corresponding to the normal shock position, and then the flow slows down and the nozzle acts as a diffuser. So indeed, in this case, the shock wave, the normal shock wave, separates the part of the nozzle divergent section, which represents the traditional DeLaval flow in the nozzle, and a diffuser, which is separated by a shock wave. By increasing the pressure ratio or decreasing the ratio of PE, the exit pressure divided by the stagnation pressure, I can move the shock position. It's also interesting to note on these graphs that if there was no normal shock wave, where would the isentropic flow be? Return the graph the middle one and the bottom one on the page, you'll see these dashed lines represent the solution as if there was no shock wave. Take a few minutes and compare the solutions between isentropic flow and the flow with the shock wave. And don't concern yourself too much with the physics of shock waves, because we'll have a lot of classes on shock waves coming up in this class. For now, concentrate on isentropic flow, but remember, isentropic flow breaks down in these cases. One final thought is that we can treat the whole flow in this situation as isentropic except across the normal shock, and we'll learn to solve these problems with a combination of shock wave theory and isentropic theory in this class. Let's now turn our attention to the mass flow rate within particular nozzles. Remember, the mass flow rate increases as the ambient pressure around the nozzle or device decreases, that is, the exit pressure is decreasing, or if we hold the ambient pressure constant and we increase the total pressure ratio. Notice I've not said anything about temperature. The mass flow rate is really dependent on the pressure ratios which drive the flow. It is easiest to assess the mass flow rate, m dot, based on the throat conditions, but not in practice. And we'll find out why in this course through examples. Now remember, a nozzle can always be measured as a mass flow rate with its density, cross-sectional area, and velocity at the throat. We can also measure mass flow rate simply by measuring the oxidation and fuel injection rate in the plenum of the nozzle. And that is true, of course, for aircraft engines or indeed rocket engines. When these flows are choked, we can write equation 272, which is m dot rho sup star a sup star u sup star. Remember, when I say sup, I mean superscript. The nozzles and throats are choked and restricted from the plenum to the throat between Mach number 0 and 1. It is possible to have a supersonic Mach number going into a nozzle, and we'll see examples like that in the coming classes. But for nozzles and propulsion systems themselves, you'll always see the Mach number being less than 1 before the nozzle. If that wasn't the case, we would only want a divergent nozzle. Can you think about why this is the case? Now remember, because Mach number is restricted at the throat to being 1 or less, we will be unable to increase the mass flow rate with increasing NPR, which we define as P naught over P infinity. Here, P naught is the total or stagnation pressure in the plenum upstream of the nozzle, and P infinity is the pressure in the atmosphere around the flight vehicle. NPR stands for nozzle pressure ratio. Remember it. Let's look at some more examples now that we can appreciate this. Here's another particular rocket engine cutaway showing the combustion chamber. These are injection plates for fuel and oxidizer. We can maybe talk a little bit more about how these work in the class, but of course these were developed over many decades experimentally and led to, of course, many of the unfortunate rocket engine failures. This rocket engine has a rather large plenum and a moderate area contraction from what we would call the area of the inlet, where my mouse is moving left to right, to the throat. In these types of flows in rocket engines, your Mach number is always 1 at the throat. That's why they've choked the throat there. Then they have a rather aggressive A over A sup star opening below the throat. Take a second and appreciate the engineering behind these beautiful nozzles. I now show a number of examples which I would like you to read carefully and try out for yourself. These involve the types of isentropic flows of chaotically perfect gases through nozzles. That is, isentropic flow through the famous DeLaval nozzle. These are classic problems which almost all aerospace engineering students try at some point in their education and career. I'm sure that in your career, many decades from now, you'll look back fondly and think about how this physics applies to many different cases. I'll show the problems now for you to try and work through. I hope you found those examples constructive, and we can talk about them one-on-one in our sessions. In this class, we looked at the famous DeLaval nozzles and their history, and who was Gustave DeLaval, certainly a contemporary figure who has influenced our society. Remember, he worked by physical intuition, and he was not aware of the mathematical theory and the so-called experiments to even prove the flow was supersonic inside his nozzles. Indeed, he had a very high pressure ratio to drive them, and his nozzles could have been designed more efficiently instead of having just the straight wall divergent sections. We then looked at the physics through a new formulation of the Mach number area relation for Convergent-Divergent or DeLaval nozzles. We then looked and started to show you what happens in real nozzles for certain pressure ratios where the back pressures can't be met through supersonic isentropic theory. Remember, there's an infinite number of subsonic isentropic solutions for nozzles, and there's only one particular supersonic isentropic solution. There indeed is an infinite number of supersonic solutions for nozzles, but indeed they are not necessarily isentropic. We saw how a shockwave forms, and we looked at graphs of both isentropic and non-isentropic flow through the nozzles. We also looked at a number of beautiful examples of rocket engines where this concept has been applied. Thank you very much for your time today. I'm Professor Steve Miller.